applied into many areas like smart cities, healthcare. So one of the great challenges is going to come from the uh, this applying these artificial intelligence techniques like machine learning or especially the deep learning. So there the basic challenge is because IoT devices are still not very powerful. So we have to look at the lightweight versions of whatever we do at cloud. But there are many other types of demands on the edge devices, what we call as IoT devices. And these are basically in terms of real-time response that many applications desire. And as the computing performance is increasing, so people have aspirations to handle a very complex task right at the edge. One of the areas of our interest is also the ambient assisted living systems, especially for elderly. And one of the major reason of applying these IoT applications there is to help these people in their day-to-day living and monitor them, especially if they have got some difficulties. So, video supervision of these people has become very important and useful, and that's where this vision computing at the edge is actually one of the major demands. And another aspect that also aids to our vision processing right at the edge is the need for saving a lot of bandwidth, because every time whatever videos we capture at the edge you have to upload on the cloud, process it there and get the information back, and then maybe you can take action on the end systems. So that is another reason that we need to avoid this whole of transmission and saving bandwidth, and over and above I told is the response. So I'll be talking of these things and how these problems are being solved, because software solutions are not that what do you call very useful. So what we have to do is that we have to look at some of the hardware engines. What we call them today is the AI accelerators, and so I'll be touching upon some of those aspects, that what is happening in the hardware accelerations that are being developed, and there are special custom chips apart from. There are some applications which actually can handle rather apply this all these GPU technologies, but they are very power hungry, very complex devices. So people have been thinking about very customized engines which are much simpler, take less of a power, less of space, and very efficient at processing of the. So Dr. Sunil, can you tell me if you got can see my slides?
Yes, sir.
Okay, good. So I'll be talking of this. I'll just put in full screen mode. Why it is not going into full screen? Let me just have a look. Yeah, it shows full screen. I'll remove gallery from this. Can I remove the gallery from here? Okay, gallery on top. Okay. So yes, so I'll be talking of various aspects on this topic, and as I told you, one of the very immediate concern for us is to provide the smart healthcare with the help of whether it is hardware or lightweight analytics at the edge, that we bring it for use in the helping the privacy and also real-time response for the people who are being monitored. Okay, so So I just told very briefly, but let us look at why computer vision at edge we have we will be discussing. Then applications that need AI at the edge, and what are those processing challenges at the edge when we talk, especially the uh, image processing, or more complex is the video processing, and what are those software solutions and GPUs or custom ICs, and there we come to the hardware accelerators. Okay, so we will be looking at these things. Now, just for I think people who have been working on computer vision, they know that there is a whole a lot of ImageNet data set available, and people have had running challenges to evolve some powerful models to handle some of those recognition challenges that this whole contest offers, and there have been different versions of these ImageNet challenges. And as you can see from this slide, right from 2011, there have been different models evolving. The one AlexNet has been very popular model of deep learning, and then followed by VGG, then Google Nelit, and there are many more which have been coming. And recently, I think the mobile net has come. So this is the whole process. And if you see the capability of a human being at the scale of 5, so this is the capability of human beings. So today we stand at models which are much more powerful than the human being. But we are looking at the capability of these models at the edge. So that will be our discussion. So some of the applications at the edge, as I mentioned rightly, that image recognition, there are certain applications where, for example, in smart city applications, you can think like people recognition is a very important tracking people. Uh, Object detection are much simpler techniques available. Then one of the applications is natural language processing, where people can interact, and of course the visual analytics has more challenging, enhanced with the video analytics, and there are many more other applications you can think about, the classification, hierarchical classification, even on voice processing. There are, you can characterize people based on the voice. So, and there are many more, face recognition, a number of applications which everybody wants to move from cloud to edge. So some of the deep learning models you saw in the graph, and this is how they have been evolving. And MobileNet is a recent one which has just been talked of, and there are many more going to evolve. So just if you can look at the capabilities, of course, it's a little older, but you can see how these various models, starting from AlexNet, from Alex Krzyzewski and their group. Geoffrey Hinton is one guy, probably you know that he is a basic developer of the neural network, very old days. And then this ZFNet, Google Init is another one, very powerful one. And this is what it shows, the how many parameters in the last column, these various models that are becoming more and more complex. So the number of parameters that can be handled is also becoming higher and higher. So, so we will be some of the platforms that so far we have been familiar with. I think mostly these have been deployed on the cloud only. So TensorFlow is a very popular one, Cafe, PyTorch, Oracle Machine Learning, then AWS. These are various platforms that are available on cloud, and we have been, playing with them, solving many of our problems. But recently, the some of these platforms are being customized to work at the edge. And in that, if you look at Intel OpenWindow is one which has been customized, and today you got hardware also compatible, which can be deployed using Intel's OpenWindow technology in software on the edge. Similarly, Edge Impulse is another platform very popular, which is can be optimized to map your problems on any particular model of deep learning. and customize for your applications. TinyML is, of course, is another very powerful tool that is suited for the edge processing. So many such platforms are gradually coming up and they are being customized for edge. So as I said, some of the demands that edge presents to the hardware or software solutions for running these models. First is we have more, I mean, about 60% of the devices are all battery powered. So power is at premium, and you have to have a very low power of processing these engines. So we'll discuss that few milliwatts of the power is something that is really desired continuous power consumption. We need a very small size of the hardware because they should fit into the small edge devices that we can think of. The cost has to be very affordable because we have to have hundreds and thousands of devices that need to be deployed on the network. And many of the typical powerful algorithms that are around, they have to be, uh, evolved in the lightweight version so that they run faster, they take less space on the code and the memory. And as I said, privacy is another very important. So if you collect all the data at the edge and then upload onto cloud, there is always a possibility people will hijack the data, they steal the data. Especially, as I said, in the smart healthcare, this is one of the major concerns. Uh, Even though these ambient assisted living systems have been evolved by in European mission programs, they are not been very popular because of this reason that privacy is the top concern, and people don't like to share whatever their activities to be monitored and stored in the cloud. Reliability, of course, is an important area aspect, and we have to have less of a network traffic if we can do the things at edge. So I have just tried to put information about some of the leading hardware accelerators. So the processors which are customized to work at edge, but offering and also running the all the popular models that we are familiar with. And you'll see that the various performance parameter we have already seen. So some of the these processors or the systems on chip, they are actually more focused on vision processing, but there are some set of processors which we'll see are also there for a much lower end like voice processing and things like that. So we'll just have a first topmost one is from Intel. It was developed by one company, Mobids. Intel has acquired that. Then we have got NXP Semiconductors, another famous microcontroller manufacturer. Then there are many companies which are totally new in this domain and only are there to handle this vision processing at the edge. So Xmos is another company only developing process for this purpose. Texas Instruments is another popular company. We know they have been there in the microcontroller space for a long time, and they have come out with their TDA4 VM engine, which is more suited for vision processing at the edge. KL520 is another processor from Neuron, which is a company only working in this area of vision for the edge. Another one is GTI Technologies, what we call as a Gear Falcon, which they have developed the processors only for vision at this edge. A very powerful technology from US. I think this is the latest technology on edge accelerators for AI. Hilo is another one very important and famous solution provider from Israel. Jetson Nano is, I think, most of the people working in IoT domain, and especially for the vision and image processing applications, know about this very affordable device we have got. And there are some more devices which are not so well known, but ATA computes ECM 35352 is one processor, and they have got the solutions, very affordable solutions available. NDP 100 is from Sentient, is a very powerful processor, mostly for voice processing. Gap 9 is from Green Waves, a French company, and Kriya K26 SOM is a platform developed by Xilinx to handle the vision at the edge. So these are some of the popular um, accelerators which are working at the edge to solve vision and other demanding challenges of the processing. So this is how as I told that there are either the standard GPUs being there, CPUs of course are not really meant for handling the video or image processing at the edge. So people have been trying to put the GPUs which have been more popular, high performance machines which are mostly promoted by NVIDIA, and FPGA based accelerators is much more custom type of processors that are being developed. And the last category is the ASICs. So these are purely custom engines for processing the vision, and we'll see all that 8 to 10 processors that I had discussed. Some of them fall in the ASICs category, some of them fall in the FPGA category, and some are based on GPUs like Jetson Nano, and CPUs, of course, they are not capable to handle image or vision at the edge. So we have discussed already what are the various reasons that people are gradually now migrating all the processing to the edge. People working in the cloud computing arena, they know that after the earlier cloud computing um, period, gradually companies realize that they have to have their own cloud right at their own premises. So there have been hybrid cloud culture, which has been more popular these days, and IoT or the edge is going to be a next revolution, because almost all the processing that cloud can handle will be getting transferred to the edge. So you'll see that today people say that in coming a decade time, you'll find around 70 to 80% processing happening. Whatever it's be, it's image, video, voice, whatever, processing will happen at the edge only. So various reasons we already discussed. Real time is meaningful for many of the applications that are around. So this is how, of course, people working on, and this is not only for the edge, but it is in general deep learning evolution that has happened starting from AlexNet and today to going to MobileNet, more complex algorithms. So these all now people are trying to migrate them to the edge. So just to give you an idea that the MobileNet, the latest model that is available to be used at the edge, if you deploy that for any particular given problem at cloud, so for solving a given problem, suppose it takes 10 milliseconds. Now, if you put that thing at the edge, you will find that it will take at 2.5 times. Of course, it depends on the application, but it is at 2 to 3 times more than the what we need the time at cloud. But if you look at the other parameters, the latency. So the cloud, if because of the network transfer of data, use data particularly for the video, will take a lot of time to transfer to the cloud before it is processed. So 200 to 1400 milliseconds of time it will take for the data to be transferred to cloud. Whereas at the edge, so cell phone is, you can say that it's basically an IoT device right at the end of the whole internet, and we call it the edge. So cell phone is an edge device, and there is hardly any delay, because the moment your video is available, it is immediately processed, though it takes 24 milliseconds. So that's the only delay you will find that it will take to get out of the results and apply. So for example, the one simple application you can think of is the face recognition, as today most of the mobile phones are offering as a locking mechanism for your device. Earlier, people used to use the finger as a uh, thumb impression as your locking mechanism, but today people can lock your device or unlock using your face. So this is one simple application one can think. So suppose you want to now um, use this face recognition, but implement on cloud. Suppose your device is not powerful. So uploading whole of your face image to the cloud, processing, getting back will take quite some time, which we cannot really afford today. So it has to be immediate, and that's where you can see this application of mobile net for this application. So it's almost instant. So this just gives the importance of how fast the processing at edge can be for many of the applications that today we can think of. So we need not repeat the whole thing. All these applications, even though earlier they were based on the cloud processing, but people are now desiring that most of these be available at the edge itself. So taking care of all those parameters of response, privacy, and things like that. So you can think, I think a deep learning is just not yet ripe for taking care of many of these applications like augmented reality. We still cannot envisage at the edge, but I'm sure with time it will happen. So if you look at the, we will look at these accelerators that I listed earlier, and you will find that some of the typical building blocks or the innovations in the architecture that are happening are actually listed here. So you will find many custom processing blocks like matrix multiplier, dedicated hardware for multiplying big matrices. DSP cores has been one of the main building block of these processors, and this TI's processor that we mentioned does make use of DSP core along with the other MMA type of custom hardware. FFT, DFT, these are all Fourier transform computations that are needed many a times, and there are custom dedicated blocks on these systems on chip SOCs or custom processors that are being developed. They will have such blocks to handle the processing at a faster speed. So there are of course logic blocks very standard, and but there are much better logic blocks, much more complex logic blocks, which form the part of the algorithm. So they can be built and put on the SOCs, and very powerful and configurable IO blocks can be also major part of some of the architectures, making it more, very powerful, configurable. Then, of course, neural network accelerator, neural network blocks are the standard blocks, but many of the designers have put them in a very configuration, very flexible way, so that they can be actually reconfigured to fit into any of the deep learning model. So they are not standard neural network, but I think they are reconfigurable neural networks. You can connect their weights, you can, their connections can be reconfigured, their weights can be reconfigured. So very powerful neural network architectures are being used by some of the chips in this presentation that I'm going to talk about. There are special array processor blocks or vector processor blocks available in this, and we have got different types of codecs, be it for video, be it for voice. They are available so as a standard building blocks of these accelerators. See, then only we can think of reducing the power, reducing the size, and making the processing faster. So, so this is just one building blocks of the NXP processor But I think I will leave that right now and go to the further thing. So NXP's processor is, you can see this is how it is, you know, uh, this is of course a typical application of the NXP processor that is applied in this case. So we will start with this first model of Intel Mobids, and it's basically a Irish startup in 2016. They came out with a ASIC for this machine learning, and this has been enhanced now with the third generation processor, which can handle the vision, and it offers 1 tera operations per second. So this is the power of processing that this chip offers, and they have to be low power. So this processing power is at a much lower energy consumption, and this can configure any of the models that we just discussed, which has come to the solving of image net challenges. So one can, based on the application, one can take up any DNN and configure on this chip. Uh, the simplification and how the faster processing of these things happens is that most of these chips will use integer weights, which are used for the computation. But some of the applications also demand floating point processing. So 16-bit floating point processing is also possible on this chip. And there are many other different cores which are dedicated for handling this. So this is one processor very popular, and it is supported now by Intel's OpenVINO. So one can easily, and this hardware is available at a very reasonable cost. So one can easily implement solutions on this platform. So this is just a glimpse of how this Myriad 2 looks like from inside. And as you can see is that the memory on almost all these accelerators, memory is not looked at as separate memory, but it is a much more integrated memory, so that the transfers from memory, read-write operations do not take very specialized timings, but they are ingrained. So one does not really look at the memory as a separate interface, but it is the embedded in memory that is there in most of the designs you'll see. It's been the one major innovation. So NXP's semiconductors, I told that this is one of the, so it offers 2.3 teraflops, tera operations per second. And of course, there are many, but one thing is they also take this ARM Cortex M7, which is also used for real-time response systems. And one can take the voice processing also on this using the different types of codecs. But in this case, it is the DSP core that is used, and it is part of the NXP's a major edge computing platform called EdgeVerse, which can use this processor easily and give the very affordable solutions on the edge. So a more detailed block diagram of this NXP's processor. Of course, we'll not go into this detail, but you can see some of the blocks that we discussed. They are like neural processing unit is here, and there are video codecs and various other hardware blocks like PLLs. These are much simpler hardware blocks. So the interfacing, the I/O is also very powerful here. You can see here that there is a lot of variety of I/O, and so that one can configure based on whatever is desired there. So that way is very powerful chip. And next chip is coming from XMOS. Is a, of course, a low-end device because it can't handle vision. So we will not spend much time on this. It's more for voice-based processing at the edge. So there are many applications for voice to be deployed, and this of course, makes use of the vector processing engine available here in the X-Core AI chip with the 16 cores of they have got the basic logic cores as we discussed, logic blocks. So these blocks also have IOs, DSP, and control functions. But as I said, this is not very powerful yet to handle vision. So we'll just, but one thing interesting is that this is the chipset being used by Alexa. So Alexa is a very popular device, edge device these days, and we put use them in our houses. So Alexa is basically based on this Score I chipset. So okay, we can skip this because so we have now next processor is Texas Instruments. It's basically a deep learning accelerator, and it has got one of the building blocks is the DSP core of 6 C7XX, very popular DSP processor of TI, and it also uses a matrix multiply accelerator block and offers an 8 tops of processing with a 5 to 20 watt of consumption, and it can handle overall 8 megapixels per second, and that can of course can have a mix of cameras with low resolution, and additionally it can also do the lidar processing, radar, and ultrasonic sensors. So you can imagine that this could be a very suitable platform to be applied for the uh, self-driven cars that is becoming gradually much more attractive solution in advanced technological companies. So very powerful, and one of the intent of this basically has been to enable the self-driving cars. KL520 is another processor handling neural network or deep learning models, and this one is particularly suited for reconfigurable CNN modules. We will come back for the questions. Sweta, you raise your hand, but let me just come back once I finish off. It will be better for the discussion. And mostly it is handling only image processing and particularly the facial recognition applications. And thus this can be a suitable device for smart homes, smart healthcare, security systems, and also the mobile devices. So the performance is very good, zero point 0.3 tops, but at zero point 0.5 watts. So that power is very low, and that's why this is suited for these applications. Hilo is another very powerful processor, edge IO processor with the 26 tera operations. So it can handle very powerful applications, and of course the wattage also is not very high. You can see here is a 2.5 watts for this sort of performance. So it's a very excellent power consumption, very small size, and they have got specialized data flow architectures for implementing the neural networks. So we'll have a quick look at the processor architecture. You can see here the top one is the neural network uh, connectivity, and how this whole connectivity of neural nodes and the connections is mapped into the architecture that you see at the bottom. So this is how these whole nodes and connections are mapped in the. So this is only showing the one aspect of the uh, processor. There are other support, but this shows how the data flow architecture is taking care of the neural network propagation of the learning and also the reasoning. So just to give you a glimpse, Silo is a very recent processor. So I just try to put its performance, how does it compare with some of the existing hardwares. So NVIDIA Jetson Nano, then the NVIDIA another platform called Xavier NX. So this is comparing the high-low performance for a given application. The models that are demonstrated here is ResNet and MobileNet version 1 and the YOLO version 3. So for both these three models, you can see the performance. The high-low processor is really very powerful in a majority of applications and significantly higher compared to the NVIDIA and Jetson Nano. So we come to the very popular hardware for edge, Jetson Nano, and obviously you must understand that this is built around the GPU cores. It has got 128 GPUs and the offering zero point 0.5 teraflops. So it's not tera operations. Mostly these are integer operations, but here it is teraflops, floating point operations, and consuming hardly 5 watts of power here. Uh, this also has got it's basically a heterogeneous architecture. So you have got a quad core ARM also to support the other activities apart from the your GPUs. And it can easily be supported by their CUDA platform, which can be used to implement any applications which based on an excellent set of libraries that are available to optimize the performance of the software on this platform. So very popular one. And this is basically architecture is based on the Maxwell generation, is a second generation of Maxwell processors, which are GPUs, and it is called streaming multiprocessors. Uh, of course, the earlier version of their GPUs was called Kepler, and this offers some much higher performance compared to the NVIDIA's Kepler devices. And there are many architectural features which have been taken right from the Maxwell first generation, like control logic partitioning, workload balancing, clock gating, instruction scheduling, and in-memory processing. So all those features are taken to build a next level of processor. So this is coming to another very powerful device called Lightspew from Falcon Technologies. It is called GTI in brief, and it's basically also a design which is called processor in memory. So it's a processor, but inbuilt in the memory structure itself. So you don't, again, as I mentioned in the earlier one of the cases, that you don't have a separate memory so that you have to make read write operations, but it is ingrained. So the processing happens. So you can imagine that your nodes and the connections are all in the memory itself. So they are mapping. So there is no separate. So that's how you can speed up the computations. So this device offers 2.8 tops at 2 to 4 milliwatts. So extremely low power, and that's why it's becoming very popular. And in terms of the latency, the processing is available in every 4 milliseconds. So very fast, and enough memory is available. So complete models can be fitted on the chip. So you can think of if you take mobile net, this is having, I think, a large number of parameters we have seen in the previous slides. So all those model parameters can straightway be fit onto the single chip. So some of the aspects of the architecture is basically neural network with a domain-specific architecture, and it has got a dedicated matrix processing engine, and there is a efficient AI processing in memory. So these are the two concepts unique to this chip, and I will see in the next diagram. It offers 24 tops per watt. So this is the one of the parameters of performance. Tops per watt is a criteria. So these are the two architectures, domain specific architecture, and the other one is the in-memory computing, which make this chip very unique in its architecture. So ATA Compute is another device which is based on the ARM Cortex M3 and NXP's Cool Flux DSP, and added with some more glue hardware, which makes the neural network models implementable in this chip. So it is the lowest, in my opinion, 100 microwatt, but of course it is still not designed for vision processing, but image processing, yes, it can be handled. And that is one of the more important applications for this chip. This just gives a picture of the ECM chip and how a particular board that has been made and available at very low cost is available. So you can just see the two basic parts of the core DSP and the uh, Cortex. Sentient processor is another very useful device to be operated at edge, and it also has got the same concept of processor in memory architecture. So using 140 microwatts in the maximum consumption processing capabilities, and the low end application like voice or some textures that can be easily handled by these devices, and some of the applications that one can envisage based on this processing. So this is a broad architecture of this DP100 device. You can see here is a neural network model that you can fit here, and there are other glue logic and the other interfaces like audio, and you got the data RAM. So these are all integrated together. That's why we call it the in-memory process. The last but not the least device will be the gap green waves. I hope I have another 5 minutes for this discussion. So this is another very useful device recently becoming popular, and it's basically a French startup which has come out with a dedicated architecture application processor for handling the uh, edge processing. And this can take also not vision but images and sounds it can easily handle, and works at a very low power. That's why one can think of putting on a battery powered IoT devices. So the just one benchmark of MobileNet version 1 is put here, which takes hardly 12 milliseconds, and that too in a very low power, 806 microwatts per frame per second. So you can compute for this given application. It's very low power, and this is a very complex architecture. You can see here there are multiple cores here, 8 cores are there which are put together in a pipeline manner, and that's how this acceleration happens. So we will not have time to discuss, but you are always welcome, and you can go to the supplier sites where details of all these architectural aspects are available for those who are actually interested in the architectural aspects. So last device I will discuss will be the Xilinx Kriya K26 SOM Edge Vision processor, and this is a device. Of course, the reason has been that because everybody wants to put the processing at the edge, so they Xilinx also try to use their Zinc Ultra Scale MPS architecture, multi-processing SoC they had beforehand. So they tried to put that together on a chip with the neural network model, and so that you can handle the deep learning models for the vision processing. So very small and very powerful device. But of course, as you know, the all the solutions that come based on the FPGAs. This also has an FPGA based device like Zinc uses their FPGA devices. So it's a I mean, if you talk of scale of production, then this will not be a very suitable one. But for some applications which are not to be rolled out in a big numbers, I think one can think of putting this Kriya K26 as a solution, very efficient solution for that matter. So, so it has got a sub-millisecond latency, very powerful, and it can run many of the deep learning models that we have discussed, customizable, I mean, and the peak performance of if you use the deep learning block B31. So there are different types of deep learning blocks on these K26. So if you think of 3136 block, then it has got 0.94 tops, and the other one higher end is also available on this K26. So one can have 1.2 tops of operations. So of course, this offers at least 3 to 4 times the processing power of Jetson Nano. So you can imagine how powerful this Kriya is, except the cost on that front, it is not that powerful. So that brings to me to the end of this discussion. And of course, we have just discussed about all the hardware that are available on the edge. But I foresee that today, whatever platforms, whatever models are available on the cloud, that you are able to do vision processing, gradually you will find that many of them will come in a lighter weight versions, and they will be available on the edge in not a long time. So you will see that gradually happening. So whether it is Intel's OpenVINO, which is much more powerful, can run on their processor, Google, Microsoft's solutions, all those models that are available, like TensorFlow or whatever you talk, they will gradually come in lighter weight versions, and you will find them on the edge. But that's a major challenge, because optimizing software to run on edge is going to be a big challenge. So, but I see that to happen shortly. So, with that, I will almost stop. Try to give a glance on whatever, and as I mentioned, all of these accelerators that are I mentioned, every of the product available for your prototyping, and of course production, you can talk to the company, but for prototyping they are easily available on any of the electronic selling platforms uh, that you are familiar with. So that's all I wanted to say with you, and now I'm open to questions. You're most welcome if there are specific questions.
Yeah, participants can ask questions.
And of course, you are most welcome in case you don't wish to talk now. You are most welcome to come back to me on my email ID that I said, or you can also call me. I'll try to respond, but email would be a better choice. And if there are any specific queries, I'll be happy to answer right now or maybe later.
Thank you, sir, for this
Okay.
informative
Thank you. It
session.
was a pleasure sharing my thoughts. Thank you so much.
The participants are just going through the software part, and I think it's very important to know for them what's going behind it and what kind of innovations are going on, so that the data sets they are talking about, the huge size which they are, how it can be handled with the minimum energy consumption and more smoothly. Thank you again very much, sir, for highlighting the very pertinent issue. And this is something which generally machine learning, we can say engineers or data scientists, they don't bother actually what's going inside the machines, but it's equally important. So thank you
The
again, sir.
important thing is, as I told, that almost all applications today we are comfortably doing in cloud, but you will see gradually the need is at the edge. You know, the need of this processing is at the the location where we are doing the application, and that's the
Yeah.
reason I said most of these processing or deep learning model that we are running at cloud, all those applications would actually end up coming to the edge. So that's where it's very important that we must now explore how to deploy these complex models at the edge to solve the problems right at the location where they are needed. That's very important, and you will see that gradually people will migrate to edge with all these evolving models. So
finally,
anyway,
finally, I would request participants to please switch on camera and have a group photograph.
so I'll just stop sharing and
Done, sir. Thank you, sir. Thank you so much.
Thank you very much.
thank you. All the best.
Thank you, all the participants. We'll meet tomorrow for the next session at 10 a.m.
Thank you, sir.
Have a good day.
Thank you, sir. Thank you, sir.
Thank you, sir.